let me start by reminding what we did last time. And then I will come to, well, first I will derive Einstein's equations. And then we will discuss AdS space. So today what I want to do is to derive Einstein's equations. And then talk about D-branes a little bit. And arrive at AdS CFT correspondence. And then some properties of the AdS space. This includes the entire program of today, so it's this lecture and the lecture afternoon. And then some calculations of correlation functions of CFT. CFT is conformal field theory. I will explain what that is by AdS, by the AdS rule. So, but first, let me remind you what we did. So, we were talking about general relativity. So, the general principle is to start with the equivalence principle, which is essentially saying that there's no way to distinguish how gravity couples to energy or momentum of a particle from essentially an accelerating frame. And from that, we arrive at the statement that since all of the particles with different kind of momentum, with different energies should move exactly in the same universal way under the gravitational force, this naturally can be realized by the fact that the space-time geometry is curved. So equivalence principle implied curved space-time. And then we have a mathematical theory, which is the differential geometry, that describes how to do physics in curved space-time. So I wrote down the geodesic. We derived the geodesic equation. You derived it in a homework problem, etc. So now what we know by now is that if I give you a curved space-time, you know how to calculate, you know how to find, for example, how a point-like particle moves in a curved space-time. Okay, so you know how to derive the motion of a point-like particle, but you don't know. So the opposite question is the following. So where does the metric come from? Okay, so the metric is curved because of the mass distribution. I mean, space-time is curved. There's a non-trivial metric. Curvature comes from the mass distribution in space-time. For example, if on Earth there's gravitational force and it curves space-time around it. Okay, so all these line segments are different at different locations of space-time because of this huge mass of the Earth. So then the question is how to obtain the curvature from the mass distribution, and this is given by Einstein's equations. So there are two different ways to arrive at Einstein's equations, and one I will talk about both of them. So one of them is the physical approach. This is the approach that Einstein took. So this is Einstein's approach. The other one is more formal, but I will also talk about that. So in the Einstein's approach, what he was asking was that, okay, so now we know that we all knew before from this equation, gravitational force equals just mass times the gravitational, the derivative of the gravitational potential. Right? So this is just Newton's equation. So he tried to generalize Newton's equation. So starting from Newton's law, we want to generalize that equation in such a way that it preserves generalized such that generalized such that preserves general coordinate transformations. So that if I work in a curved spacetime where I have different local patches of different coordinate patches, so I should be able to write down some general equation that satisfies general coordinate transformations. That's the invariant under general coordinate transformations. So that thing is not invariant. So let's start. So the first thing that you can think of is the following. You can start with the Boson's equation. Boson's equation states that the gravitational force is due to mass distribution. So let's the gravitational field is some constant that I will call kappa times the mass density, right? So rho is the mass density. So this is the same, oh, there's a minus sign. So this is the same equation as you write down in electromagnetism, of course. This is just Boson's equation. It tells you how, in the case of electromagnetism, how the charge density generates a potential, an electric potential. In this case, it's just how a mass density generates a gravitational potential. So what we want to do now, but this is not general coordinate environment, because this is just this derivative here is only it's just d squared in my old notation. It's just d squared. So it's just del. Okay. And it's only in space. It's not in space time. So what I want to do is first. The mass is not invariant, so I have to replace this with the notion of under special coordinate transformations, for example, under Lorentz transformations. Mass is the same thing as energy or momentum, so there's no distinction between them. So energy it's the same thing as mass. In the case of when there is no momentum, if particle not moving, energy is the same thing as this is just d equals mc squared. So I'm setting c to 1, of course. So this means that, this led Einstein to write down an equation. Well, a natural thing to replace this is the 0,0 component of the metric. So what he wrote down is the just 0,0 component of the metric, d squared acting on this equals some kappa times, and he replaced this mass distribution by energy. And energy is given by the zeroth component of the energy momentum tensor. So this is the first thing that you can think of. And then if you write down an equation like this, it's immediate to think about the generalization of that, so that you have instead of having just 0, 0 indices, you have all of the indices in both sides, so that it transforms perfectly in a nice way. So what you can do is you can write down something like del squared g mu nu equals kappa t mu nu, where this is the energy momentum tensor. Okay. But this is still not covariant. So what we have to do, as I mentioned before, if you want equations that transform nicely under coordinate transformations, if you have a partial derivative, you have to replace these partial derivatives with covariant derivatives. Okay, so that this is a tensor. It's just by definition, it's defined in such a way that it transforms nicely under coordinate transformations. Okay. But this side doesn't transform nicely, so you have to replace this thing with the general, with the covariant derivative like that. Okay. So then this looks okay. This transforms nicely. The only problem with that is that this is trivial, because as you show, or you were supposed to show, in one of the equations, that del acting on g mu nu is 0. So this is not nice. Then his idea was that, okay, so maybe on the left-hand side we should have something else. On the right-hand side, it's clear that we should have the energy momentum transfer, because that's the most general and covariant object that describes mass distribution, energy and momentum distribution. Okay? But on the left-hand side, what you need is something that depends on the metric, because metric defines, this is the quantity that we want to obtain, the metric. And it is clear that we should have a second order differential equation. So what we need is something that contains the metric and that has two derivatives. And we know such an object. And that object is obtained from the curvature tensor. So in the last time, I think the point I spoke was that I didn't write down the curvature tensor, right? So I started talking about the curvature of space-time, but I didn't arrive at the curvature tensor. So what I was doing there was that I wrote down, okay, so if you consider an infinitesimal bed, like that, you start at some point and then go around some infinitesimal like delta A, delta B bed like this, like that. And this is, suppose that this is generated by some vector A mu, this is generated by B mu. And then if you think about the vector at this point, and then come back at the same point, if this space-time is curved, you can convince yourself, like by thinking about the sphere, that this should come back with some non-trivial angle, non-zero angle here. And well, that angle is described by the curvature of the space-time. And the equation that we have to write down is well, so the transformation of this vector that you started with is something like R mu alpha beta gamma A alpha beta B gamma delta A delta B. Okay, so it should be like this is just the area of the infinitesimal loop here. But the important quantity that describes curvature was this. And so what you can do, I'm not going to derive this, but I will just mention the way to derive this quantity is to parallel transport. So take a vector. Okay, so I will mention what parallel transport is. So parallel transport is you take a vector in a curved space-time like a sphere, for example. You take a vector at some point, okay? Like for example, the tangential vector. And then or some vector with some angle theta, and then you take this vector along this curve. Okay, parallel transport is defined along some curve, x mu. You take this vector, transport it along this curve by keeping this angle constant. Okay. This is the definition of a parallel transport. And if you parallel transport a vector along this loop and come back, so the parallel transport is defined by around the curve. On a curve, x mu, it is defined by this equation. So, right, dx mu ds. Suppose that this curve is parameterized by some s, the covariant derivative, okay, acting on some quantity like the vector alpha, whatever. It should be zero. So this, if there is no curvature, so this you can replace this covariant derivative with normal derivative, and that means that the vector doesn't change as you transport the vector along something, right? So this is how you define it. But if the only thing that you have to do in a curved space is just replace this derivative that you would have in the normal space-time, I mean in the flat space-time, with some covariant derivative. That's all. And you know the definition of the covariant derivative. Then what you can show is that this should be given by essentially the commutator of delta alpha, delta beta, acting on E mu. And giving rise to some change from this, you know how these derivatives act, etc. So you can read this in one of the references that I will give, or the books. But the end of this result, end of this calculation, it's not a very hard calculation. The end of the calculation is that you find this nice equation for the curvature of the beta gamma, which I never remember. Well, okay, so it's written in one of the exercises they do that, so I don't, for the sake of our camera, I will just write it. Remember that in this covariant derivatives there was this curve connection here, so what you find is as a function of the curvature, depends on the curvature. Okay. This was the curvature transfer, nice. So what I want to do now is to come back to Einstein's equation and obtain a quantity to replace this that depends on the metric. This depends on the metric, you know. I gave it, this is the metric connection, it depends on the metric. The equation was written last time. And to obtain a two index quantity out of this. So you can obtain a two index quantity by just contracting, for example, this index with that index. This is the kind of symmetric way of contracting the indices. And then you arrive at this answer alpha gamma, r mu, alpha mu, gamma, okay, by this contraction. Contraction doesn't change the fact that this is a tensor. So in one of the problems, I think you have to, you show that this is a tensor. It's clear that it should be a tensor by just this equation, by definition it's a tensor. Because this is a tensor, this is just a vector. These are all vectors, so these are multiplication of vectors are tensors. And this thing, difference between two vectors is also a tensor, because both of the vectors are tensors. So this one should also be a tensor. So you don't even have to show that this is a tensor, it's a tensor. And when you contract two indices of a tensor, you still obtain a tensor because the way it transforms, this general thing transforms, is that you remember when the upper index is transformed like x prime over x, and the lower index is transformed like x over x prime. And in this case, you are contracting these two indices, so you arrive at a Kronecker delta function, so which is just still a tensor. So this is called the Ricci tensor. So then, well, Einstein wrote down the lovely equation r mu mu equals kappa times mu mu, which is wrong. It is wrong because this is the energy momentum tensor, and it should be conserved. And the energy momentum tensor conservation equation in a curved space time is again the covariant derivative acting on a quantity like mu mu equals 0. This is just the energy momentum conservation.
Why do you contract upper indices with second covariant indices? Is it because?
Well, it's because of some symmetric properties of the Riemann tensor. It's I would show those symmetric properties later. But, I can give it as an exercise problem. So it's just at this moment, just take it as a definition. It's essentially they are all equivalent under the symmetric properties of the remaining tensor. The different way of contractions become equivalent to each other, so you can pick up one definition, and this is a nice one. And so this is the energy momentum conservation equation, but you can show by just the definition of this. So here's the definition. You just take mu and mu here. You obtain the definition in terms of the metric. I mean, this is the connection which is given in terms of the metric. And if you act on it with covariant derivative, you can show that delta mu acting on this side, R mu is non-zero generally. But again, in one of the problems, I asked you to prove that there is a different quantity, which is called the Einstein tensor, which is given in terms of the Ricci tensor in the following way. So G mu nu, this is the Einstein is defined as R mu nu minus, well, this covariant derivative acting on this is not zero. It generates some non-trivial piece, but you can cancel that piece. If you study that, you can realize that you can cancel that piece by subtracting a different tensor, which is just the one that you contract these two indices of the Ricci tensor, which is alpha. Okay, this is usually called just an R. This is called the Ricci scalar times G mu nu divided by 2. Okay? So this is a tensor, this is a tensor, this is a tensor, so this should be a tensor, which is nice. And then you can write down, then you can show, this is again one of the problems, that delta mu acting on G mu nu equals 0. So finally,
I understand fine. How can the derivative of curvature not be equal to 0?
how can not be equal to 0? Well, it is not equal to 0.
But
Why?
T mu is 0.
Right, exactly. So this is not the right equation.
No, okay.
That's why I'm arriving at that.
Okay.
Yeah, sorry. Yeah, I mean, I said that this is, Einstein wrote this equation first. Actually, he did write it, I think, I read it in this book of Shankar. And then he didn't apparently realize that this was contradicting the energy momentum conservation. But then he arrived at the right equation, the correct equation, which preserves the energy momentum. So now if you write this G mu nu, the Einstein tensor equals alpha times G mu nu. Then you have what you want to have. So this is Einstein's equations. So this tells you two things, right? So this tells you how, given a mass distribution or energy momentum distribution in space-time, how solving this equation you can obtain the metric. You can obtain how the space-time is curved around this mass distribution. Right. So, but it also tells you that suppose that there is no mass distribution, this is 0. You can still, this is still a non-trivial equation. So you can still have some non-trivial solutions of this equation, which is very, I mean, for example, black hole solutions, etc. So flat space is an obvious solution to this equation, because in flat space, this side vanishes. There is no curvature, this is 0, and there is no mass distribution, 0 equals 0. Okay, so it's a trivial solution. Flat space is a trivial solution. But there are also black hole solutions, like Schwarzschild black holes. That's it. It took people a long time to realize that there are these non-trivial solutions to the equation. That even if you set this side to 0, there are non-trivial solutions. Okay, so but this is the equation that we want to use. So, any questions? When this is not 0, no, I mean, what I'm saying is that, yeah, it is 0, of course. The small d is non-zero, yeah. Because this is a very non-trivial equation. It's a very, like, I mean, because this is a non-linear equation. Because you see, like, this depends on the curvature tensor. Okay, so this difference. Here, there is also G. Here, there's L1. So this is like, it is quadratic. And here you see this thing depends on G in a quadratic way as well. So there's one G upstairs, there's derivatives of G is downstairs. So this is like extremely complicated equation. Okay, so this is a nonlinear differential equation. Even if you set this to 0, there are many non-trivial solutions. This is nonlinear.
Why in black hole that is 0?
Well, there are black holes when this side is not 0 as well. I mean, you can have some. For example, if you have a charged black hole, then this side is not necessarily 0. I mean, you can if you have a charged black hole, for example, you can have an electromagnetic field distribution in space-time that is described by the energy, the stress tensor. So if you have a stress tensor, if your theory, if your Lagrangian, for example, is contains this h-squared term, okay, so this is electromagnetism, then you can compute the energy momentum tensor from this. I don't know if you did that, but you can compute that. And this is non-trivial, so you can put it on the right-hand side. You have this will depend on charge, but you can still solve this equation and you can find black hole solutions. So there are black holes that are charged on where this side is non-zero. There are black holes which are this side.
So when it's not charged,
Well, I mean, there's a mess of black.
if it's just
What I'm saying is that there's what I call a black hole is an object that has a horizon, which you know what horizon is. Okay. So you can find metric solutions to this equation when this is 0. Okay. When this GTT component of metric goes to 0 at some finite coordinate r. And this means that light rays cannot escape from that point, which is the black hole. So you can, when this is 0, yes, I will put the uncharged level. I sent me a message. Alright, so okay, so this is it. And the second derivation, I just write it down. It's very easy. So I mean, you don't have to go all this way, because I mean, once we have all this tensor machinery, tensor technology, we could have written down an action right, immediately. We could have written down this action, Einstein action. It's usually called Einstein-Hilbert action. I don't know what contribution Hilbert did. G. Newton, there's of course some Buffing constant in front. You have to write down an invariant quantity now. Invariant means that it should be a tensor, but all the indices contracted, so that there's no index floating around. So you can have a metric, determinant of the metric multiplied by the, depending on the dimension of your spacetime, dvx. So this is an invariant quantity, invariant volume form. Okay, so this you showed in one of the exercises that this is invariant. Times some scalar. I want to write down some scalar that depends on the curvature. So we have the curvature tensor. And the only scalar that you can obtain a scalar from the curvature tensor, and this is the richest scalar that can be defined. So if I put here R, I am done. Okay, so if you start with this, you can show by just varying this action with respect to variations of the metric. Okay, so you can write delta S equals delta G, well delta Lagrangian is delta G mu nu times something, and that something is actually exactly this G mu nu minus kappa. Well, this kappa is this kappa here. Let me call it. It should be proportional to Newton's constant. So let me write explicitly Newton's constant. D mu nu. This fact that T mu appears, So how does this appear? I'm not going to do this calculation for you. You can do it for yourself, but let me mention how it arises. So if you take
why do you write this on the direction?
you can write you have to write a scalar, right?
Yes. That's the motivation for writing this.
What is the motivation for this?
Yeah.
Well, I mean, you can write down different things, but this is like a kind of a unique scalar quantity that you obtain from the curvature transform. I mean, the idea is that it should depend on the curvature transform. If you write some other things, you can, I mean, but of course you can write down something like this, for example. Just a constant. And this is called the cosmological constant. And Einstein missed this constant in his first formulation. In general, you should write down everything that is a scalar. But then you go and do experiments, right? Like gravitational, like redshift, or this Doppler effect that I talked about, and some other kind of procession of Mercury, etc. So these kind of how light rays bend around some mass distribution, etc. So by looking on these experiments, these results, these observations, you arrive at the fact that this is the best gravitational theory. There are some other formulations which are not using this formulation, but which is using some. I mean, assuming that you replace the metric with some kind of scalar quantity, some phi. This is called the Browns-Dicke theory, but that doesn't work. That predicts something wrong, in contradiction with the experiments. So, in fact, yes, it is true that you can. I mean, if you are open-minded enough, I mean, you should write down all the scalar quantities. That's true. But then you go and do experiments. And this is right. Including the cosmological constant. It turns out that our cosmological constant in our universe is non-zero. It's positive but extremely small. Almost zero, but it's positive.
Does it change?
The cosmological constant is constant by definition.
Because constants sometimes change.
Yeah, I mean, people are actually considering this option, yes. It's many. But I mean, in this equation, it's obviously constant. So, if you want it to change, you have to make this some kind of a dynamical field that changes adiabatically as the universe expands. And there are papers that you can find that are discussing that scenario. Okay, but at this level, I just need a constant change. All right, so this is Einstein's equation. Okay, so how to arrive at this equation by just this transformation of the action to see how it varies? Well, first of all, the energy momentum tensor is defined by. I'm not worrying about these constants. There are some constants here that I have to put, but the important thing is not that one. So it's just the variation of the Lagrangian. Right, okay, so this is only the gravitational part. Now, in addition to that, you have some Lagrangian for the metric fields. As I said here, if you have a charge, for example, you have to write down f squared. If you have some scalar field around, floating around, you have to write down the Lagrangian for the scalar field, like del phi squared plus some potential, etc. So if you have some mass distribution around, you have to write it here. That is Lagrangian for the mass distribution. And energy momentum tensor of that mass distribution is given by the derivative of this metric Lagrangian with respect to the metric. Okay. So this is the definition of the energy momentum tensor. If you use this definition, and if you look at the variation of this object with respect to g mu nu, from here you would get t mu nu. From here, square root of g times r, you would get this one. So then you would arrive at this equation. it's not obvious, but this is not a very hard computation. It's just a page. Okay, so you can do this as an exercise if you're interested. Right. So this is the second way of deriving, by just starting with the principle that the action that we write now should be invariant under general coordinate transformations, and then you write down all the terms that you can have that depends on curvature and method Lagrange, etc., and you arrive at Einstein's equations. Okay. So from now on, I will just stop talking about general relativity and start talking about the AdS CFT correspondence and how to arrive at AdS CFT correspondence from string theory. Okay. So this is unless you have some other questions. So GR stops here.
What do you mean by charges? Is it electric charge or mass?
By charge, I meant electric charge.
So here you said.
I mean, electric charge is like an electric field that fills the space. Right? It's an electromagnetic field. So it has some energy.
So in this element, do you include mass or charge?
I include everything. Like if you have, for example, for me, like already at the level of special relativity, the distinction between mass and energy is lost. Because right, so for me, like the invariant notion is energy.
And don't we also have mass contribution in metric because it's curved?
Yes.
So it's also
exactly.
in the R.
And it should be equal to each other. So if you think, okay, so you can think of like this. So suppose that I have a flat space. Then I put some electric field. That electric field has some, it can have some angular, you compute the electric field can have a lot of, like the angular momentum, it has angular momentum, it has energy, etc. So it has some energy that fills the space. So this total energy should somehow curve the space-time. This you can think of as the mass. So, but the right way to say it is that there is some energy distribution, not the mass distribution. Okay? But you can also think about just putting some just mass somewhere. I mean, not an electric field, but just some mass which no kinetic term. So I mean, I can put a scalar field, for example. I mean, this elementary can be something like G mu phi plus V of phi, and its potential can have something like m squared phi. This can have something, it can have this piece, and you can think of a situation where the field doesn't change, it doesn't have any its derivative vanishes, but potential can be just this mass term. So this in this case it would be a mass. This is the definition of mass. So you can have a field like Higgs particle, for example. It has a mass. And if you put, we are supposed to have Higgs particles all around here in this classroom, and that has a mass. So in that case, it will be just the mass of the Higgs particle, and it should curve the space-time around. It's very small, so that it doesn't change. It doesn't curve, or it can be just curved.
So when you said nerds of black holes, they don't have electric charge, but they have mass.
Yes. No, I mean, okay, so the mass, as I said, the way to define mass for the kind of neutral black holes is not like by putting mass by hand, but from reading it off from the curvature of the space-time.
So you don't add this element
No.
It's in R.
So in some, I mean, since you have this equation, in some sense, that where is mass? It's not very clear. It can be, I mean, even if this is zero, you can still have some. You can define mass in a consistent way. But I mean, you can do two things, right? So you can do like, suppose that there is no curvature, it is zero. First, I put some mass distribution. Then I ask what is that? What is the metric? Then I have to solve this equation. But you can also do, I mean, suppose that this is zero. I have this equals 0. But then from that I can find a non-trivial metric from which I can define mass. Okay, so I mean, I'm not going to be talking about black holes, but it's a very important thing, of course. But before going into a different subject, let me just mention some books. This is good. It has a name 1. This is a nice book. Weinberg is another book. This contains more material. It also has a name 2. And there's a book that I learned here. I forgot its name. But I mostly, read Weinberg. Weinberg is, I like one. But Shankar is nice if you just want some introduction to GR. And then it contains all the necessary information on diffeomorphism. And the differential geometry. And there's another book which contains everything that you would like to know. Wald. And this is very nice, but it's not very easy to read. So he's proving a lot of things that I just jumped over. It also has a name. Alright, so now let me come to string theory finally. Undisturbed atmosphere. Okay, so I will not explain string theory. You've heard. Well, I mean, Wolfgang had an introduction to string theory, but I agree that it was too quick, and it's not going to be very important for what I will say now. String theory essentially is just theory of strings. So you have open strings or closed strings. I mean, you replace point particles with strings, and then as they move in space, they trace some kind of word sheet, like an open string traces the word sheet like this. It's just the equivalent of what I wrote down when I wrote down a curve that depended on x. So here they trace a word sheet, so there are two variables. One is tau, let us denote them by tau and sigma, and then the action for them, the action that you write down for them is something like this. It's just called the Namu-Goto action. Instead of the invariant length, which is just ES in this case, it should be just the invariant area. Okay, so the area is given by this quantity. If you have a metric, so you embed this this nice sheet. It's called the word sheet in space-time. Embedding it in space-time means that the metric that you write down on the word sheet should be the same thing. I mean, the distance from here to here that you obtain on the word sheet, which is measured by some metric on the word sheet given by h. Say, I have denoted the metric on the word sheet by HAB. HAB d sigma a d sigma b. Sigma a sigma b refers to either sigma, let me call them sigma a. So sigma 2 sigma 1. Okay. So this runs from 1 to 2 equals the space-time metric. I'm embedding this thing in a space-time which is larger than just this word sheet. Space-time metric we usually denote by the x mu. So if you want, embedding means that the distance between this point and that point measured by the word sheet metric and by the space-time metric should be the same thing. And here you need to write down the area of this object, which is given by the determinant of this quantity. That you can write down like determinant of d mu, dx mu, d sigma a, dx mu, d sigma b. So this is the action for a string. And this has a nice, starting from this action, actually an equivalent action that's called Korolekov action, you can obtain a mass spectrum of the string, etc. So there are bosonic, this is just a bosonic case, there are generalizations by including fermions of the worldsheet, etc., etc. String theory is such a vast subject that I'm not going to be able to talk about here. The only thing I want to talk about is that
what is the difference between the metric on a worksheet and
well, I mean, if you have a worksheet, essentially what you do is you are parameterizing the worksheet, right? So you have to write down, and what you need is on the worksheet. This should be invariant under coordinate transform, the way you parameterize it. So that's why you have to write down a metric on the worksheet by changing invariance under parameterization of a curve or a sheet like this. By which I mean, if you take sigma to sigma prime, this thing transforms, this thing also transforms, but you have to write down another quantity that cancels the transformation. So you have to introduce a metric on the worldsheet. But this distance between these 2 points, measured on the worldsheet or measured when the worldsheet is not there, I mean, before you put the sheet there, it should be the same. That's why you arrive at this equation.
Is this sigma for dimensional?
Sigma is just 2-dimensional. So sigma A is A runs from only on 1 and 2.
No, I mean, like this X mu S is just.
Yeah. Like X mu. Alright, yes. So, yes. Okay, thank you for that question. So this, of course, at every point there's an X mu. And so at this point, for example, there's an X mu. There's a function not only on S, but it's a function of sigma 1 and sigma 2. And there are 4 of them. Or D of them in general. And this is what where that X angles. Okay, so right. So when you write down, for example, this is the problem set that you solved. For the point type action, the action that you wrote down was something like this, right? So the G mu dx mu s ds dx mu s ds. So in that case, this was the variable. This was our field. But it was only a function of one variable, one time variable s versus the parameter, the curve parameter. And here there are 2 different parameters. So this is our variable in this case. And there are D of them in a D-dimensional space.
And we integrate this sigma A, this sigma B. I mean, integrate.
Sure.
There is HAB also.
Sure. Okay, so, right, I mean, in this case, I have to write down those square root of H. You have to write down a volume form that is invariant under the conversion of this one. This first thing. I mean, I wasn't being very careful about this because I'm not going to do string theory. I will just do, but yes, I mean, it's the correct way to write this. This is invariant under many different transformations. It's invariant under general coordinate transformations when you take this field to some other field x prime. It's invariant under that. It's also invariant under the reparametrization transformations. So there are more invariants. But okay, so let me, well, these names should be all contain some introduction to relativity. Right, so let me come to another generalization of this. So this was a 2-dimensional sheet. Now we consider a D-brane. A T-brane. A T-brane is like this sheet is a two-dimensional grain in some sense. So a P brane is a P plus one-dimensional object. With something like a world sheet, but it has P dimensions on P space dimensions. And then, of course, there's additional time dimension. And as it moves in time, it generates a world volume that is P plus one dimension. And you can write down, by just a trivial generalization of this, you can write down an action for that. And the action that you write down is something like this, action for P brane. I'll first write it down. Here, of course, I also have to write down, this is not a scalar quantity, because it has dimension 2. So I have to write down here something, some length scale that makes it a dimensionless quantity, which is AdS squared, and that is usually people put a factor of 2 pi. So this AdS is just the length of the string. So this is just string length scale. Okay. So this coefficient in front of this integral is called string tension. So that is string tension. So similarly in the P brane case, there's also another tension. It's the P brane tension. Depending on the dimension of the brane, it should contain the appropriate number of AdS, the appropriate number of length scale. Power of length scale. And then the rest is exactly the same thing. You just write down the determinant of this thing G mu. Again, you are embedding this in space-time, which has the different coordinates. But the object itself is P plus one dimensional, that is, so P plus one is less or equal to D. D is the total number of dimensions in space-time. So this, the trivial generalization of that is just this. I'm writing down exactly the same thing. But now this A is not running from 1 to 2, but it's running from 1 to P plus 1. And then you should, of course, say, you should
Consider object other than strings now.
Yeah, this is not necessarily a string. It's a more generalization. It's like a membrane. It has more dimensions in general.
What would be the effect of tension on the
Tension produces. The effect of tension is that this is like the mass. Tension is like the mass of the object. This is like the infinitesimal mass of the object. So if the object is like if it has some n, if it has some finite size, then you integrate this thing and then you arrive at the mass of the quantity. So the effect of it will of course curve the space-time around it. If you put a P brane, it's in space-time, in a flat space-time, it introduces some mass distribution, so it should curve the space-time around it in general. So right, so the point that I want to make about this action is the following. So I will are you tired? I will continue like for 10 minutes and then stop. Is it? about this thing is that if you have a discrete, and I'm just rewriting the same thing in a simpler way. Okay, so determinant of, let me write it as determinant of this G mu dx mu dx mu. Now, if you actually, what happens in string theory is that these objects, these p-branes, plus one-dimensional branes, they don't only couple to the metric, it couples to the metric of space-time, but it also couples to some other quantities, some other fields that exist in string theory. So the action of like effective action of string theory contains other fields. It's not only the metric. How do you find these fields? You look at as I wrote down, there are all these strings that you consider, and you look at their fluctuations. So their fluctuations correspond to some particles in space-time, and these particles contain, like in this case, for example, there's the metric, the graviton fluctuations of the metric, and there's some other quantity called the d mu field, called Raman field. You don't have to worry about all these things. I'm just writing down for information. And there's some field which is a scalar field called dilaton. This is just graviton. This is an antisymmetric object. This is a symmetric object, and this is traceless. I mean, this is a trace, just a scalar. And here you have similarly some quantities, some function like a gauge field, etc. So there are all these different kind of fields. So I mean, when I wrote down something like this, I didn't use the information about string theory. I just wrote down an object that has invariant action for an extended object embedded in spacetime. But in string theory, actually, this doesn't only couple to G mu, but it also couples to these fields, this one, that one, etc. And it turns out that you can derive this in string theory. You know how to write down the correct action by using some kind of duality transformations, etc. So I'm not going to talk about these things. But the correct way to write down the action of the brane is the following. So there is still this tension, and the object couples to the dilaton field as in an exponential form. And then you have this G mu nu. Okay? I'm writing schematically, of course, there's the determinant, etc. So let me write it as GAB. So I'm defining GAB by this quantity. Right? So GAB for me is G mu nu dx mu dbx mu. Let me define it as GAB. So it will have GAB, it will have this field E. Again, when this is B mu nu, this would be BAB. Plus, it also couples to gauge fields like this. So there's some 2 pi as string square. You have to make all of these objects same dimensional, and there's something like FAB, where FAB is the one when this is F mu. F mu is just given by in terms of that gauge field. Okay, so you don't have to worry about these things. I'm not deriving anything. But you can take this as your starting point. In string theory, believe me, that correct way to write down the action of a D brane, which is sometimes called Dirac-Kornilov action, is this. Okay. So So the reason I'm writing this thing is the following. So now if you want to expand, suppose that I take a D brane and I put it in flat space-time. So it couples to the metric, it couples to this called Raman field, it couples to this gauge field, etc. Now I put it in the flat space-time, which means that I have to expand this action. Expand SP around a flat space-time that has G mu equals to the metric of the flat space-time plus some corrections. B mu equals 0 plus some corrections, so epsilon order epsilon, let's say. Okay. And I want to find what kind of action that I will obtain for the gauge field. You can still have some gauge fluctuations. The gauge fields are always living on the brane. But the curvature, I mean, the metric of the space-time that's embedded, or this field, can be set to 0 if you want to find the action for the gauge field living on the D brane in a flat space-time. Okay, so I'm just trying to find action for the gauge fields on D brane, on D brane. And then it's a very simple computation. And you can also set dilaton to a constant. Let's also do that. Set phi to a constant. That wouldn't change the action. We just normalize this quantity. And then you obtain, if you expand it, so you get a determinant of eta A of 1, eta A B plus F plus corrections. And this thing that you can easily convince yourself, because this thing is a matrix, right? So this matrix has like -1, 1, etc. 1 up to here. I'm expanding the d-dimensional quantity. So these are running from 1 to p, right? P plus 1. So these are p plus 1. This is a p plus 1 by p plus 1 dimensional matrix. But this is an antisymmetric object. So it should have, suppose that this is 0, this is 1 to p. So it should have 0, 1, 0, p, etc. So this will all depend on f. And if you compute the determinant, okay, so what you will get is that from the determinant, the terms that depend on f will come in at the quadratic order. So if you compute the determinant of this quantity, it will be like, there will be a term that comes from ones, multiplications of 1. There is 1, -1, and the others are +1, so there will be -1. Plus, there will be some, or there will be some coefficient here that I'm not deriving for you. But then you would have FAB. And this is inside the determinant, inside the square root. You can expand the square root. So remember that there was ls square. Now, I am also on top of that, if I assume that the string length is small, because remember, I'm just trying to derive the action for the gauge field that you would observe in space-time, and effective action for the gauge fields that comes from the D brane. And then in the point like approximation, which means that ls is small, ls is going to 0, you can expand that object, that square root, and you would arrive at some action would be something like this. You would have a constant plus integral of the constant plus there will be some 1/2 factor. The other quantity is some that I didn't derive, FAB, plus corrections, higher order corrections. And you can throw this away because it doesn't change the equations of motion. What you find is that you arrive at precisely the action of gauge theories. So this was only for the single D brane. You can show again. I'm not going to show it, but I will recommend some reading in a Polchinski, in a book by Polchinski, Volume 1. It's called the String Theory. You can read in the chapters, I don't remember, that if you put n of these D branes on top of each other, not only one, but n of them, 1 to n, then the action that you obtain by the similar exercise that we did is not immediate, but you can show that the action for these n copies of D branes on top of each other gives rise to an action which is given by a trace of f mu nu square, f mu nu f mu. I was calling AB, so AB. Where now these f's, this f mu nu A, this f mu nu here, and AB is given in terms of given by this. So let's say B I Ti. So where Ti is the generators non-abelian algebra gauge algebra. In this case, the gauge symmetry that you obtain is SUN. Okay, so I know that this is a little quick, but just to give you an idea, so this is one important ingredient in arriving at the AdS CFT correspondence, that if you consider these dynamics of these objects and E branes on top of each other, by a similar exercise that I did here, you can show that the effective theory for the strings that are living on this D brane is given by this non-abelian gauge theory. So I think this is a good point to give a break. And so next time I will tell you how to arrive at a different representation of the same object. Then I will write down the AdS CFT correspondence. Any questions? Alakasız değil, alakalı bir şey aslında. Ama yani tam da aslında buraya koymayı unuttum. E to phi vardı ya şurada. E to phi aslında hala orada. Ben o constant olduğu için ignore ediyorum. Ama constant değilse, E to phi şeyde değişiyorsa, bir space time'ın bir fonksiyonuysa ya, bunu burada tutman gerekiyor. O yüzden yani bu E to phi dediğim şey trace x square'ı kabul ediyor aslında.
Bu şey, phi dediğimiz bir de tamametrin trace'i olarak
bu metrin trace'i olarak düşünmek yerine ben şey olarak düşünmek anlattım. Yani ekstra bir field. Yani sonuçta bir scalar string excitation'larından gelen scalar bir